In this video, I will teach you how to solve optimization problems. That's where you find the input value that leads to the best output value. If you appreciate the content, please give it a like. Number 1. Find two positive numbers whose sum is 17, so the product of the larger and 6 more than the smaller is maximized. First, define your variables. Let's let x equal the smaller number, and we will let y equal the larger number. In optimization problems, you will always form a primary equation and a secondary equation. The primary equation is an equation for the quantity you are trying to optimize, the quantity you are trying to maximize or minimize. You have to make up your own letter for this. So it doesn't matter what letter you pick, so just pick something that makes sense to you. In this case, the problem says the product of the larger and 6 more than the smaller is maximized. So since we are trying to maximize a product, I'm going to use the letter P for my primary equation. So let me look through it again. So the product, which means multiplication, of the larger, so that's y, so it's the larger times 6 more than the smaller. So the smaller is x, so 6 more than the smaller will be x plus 6. Just remember, for the primary equation, you have to make up your own letter. You're not setting this equal to 0 or something. The secondary equation is some other relationship between the two variables involved. In this case, that's given by the first part of the sentence. Find two positive numbers whose sum is 17. Since the sum of the two numbers is 17, the secondary equation is x plus y is equal to 17. We have learned that we can use the first derivative test, an f prime, or in this case a p prime sign chart, to identify relative extrema, relative max, or relative min. When you're doing an optimization problem, you're actually looking for the absolute max or min, and we normally use a candidates test for that. But optimization problems are a special case because they almost always involve only one critical value. And when you only have one critical value, you can actually use a modified first derivative test to find the absolute max or min. So that's what we're going to end up doing on this problem. Because we want to make a p prime sign chart, we really need one variable here, an x and a y. You can't make a sign chart from an x and a y. It needs to be all x's, or I guess you could do it with all y's. That's where the secondary equation comes in. Let's solve the secondary equation for y so we can substitute that in and turn this into an expression that has only x's in it. So subtracting x from both sides, we have y is equal to negative x plus 17. Now we can substitute this in for y. So we have p is equal to negative x plus 17 times x plus 6. Now I don't feel like doing the product rule, so I would rather rewrite this by foiling this out. Let's do the double distributive property to get rid of the parentheses. So p is equal to negative x times x is negative x squared. Negative x times 6 is negative 6x. Inner, we have the 17x, and 17 times 6 is 102. Combining the like terms in the middle, we have p equals negative x squared plus 11x plus 102. We need to take the derivative so we can make a p prime sign chart. Going term by term, we have negative 2x, and the derivative of 11x is just 11. So very simple. To make the p prime sign chart, we need the critical values where p prime is equal to 0, or where p prime is undefined. A polynomial is defined everywhere, so we just need p prime equal to 0. If we set this equal to 0 and solve, I think you can probably do this in your head and see we're going to get 11 over 2. Here's the work that I did in my head just then, just in case you needed to see it. Set up your p prime sign chart like this. Make sure you label it as p prime. I put 0 as the lower limit of the domain because we were told to find two positive numbers, so x must be greater than 0. Also, there's no way that x can be bigger than 17 because the sum of the two numbers is 17. So the biggest that x could possibly be is 17, and that's if the other number, y, would be 0. So we do have these limitations on the domain. Now we need to decide whether this factor is positive or negative in each one of these intervals. To the left of 11 over 2, imagine plugging in 0. This would go away and we would have positive 11. So for values of x less than 11 over 2, this expression will be positive. For values of x between 11 over 2 and 17, this expression will be negative. For example, imagine that you put 7 in here. This would be negative 14 plus 11. That's a negative number. This is the first derivative test, and normally we would say that p has a relative maximum at x equals 11 over 2 because p prime changes from positive to negative. Unfortunately, relative maximum is not good enough. We are trying to maximize p. We need to show that p has an absolute max at 11 over 2, not a relative max. Luckily, this is a special case where p only has one critical value on its domain. Because there's only one critical value, we can actually use this sign chart to make a stronger statement that p has an absolute maximum at 11 over 2. That's because if there's only one critical value, then p prime is divided into only two intervals, to the left of 11 over 2 and to the right of 11 over 2. Where p prime is positive, p, the original function, is increasing. Where p prime is negative, p is decreasing. Since we only have two intervals, we can see that p is increasing the entire time to the left of 11 over 2, and then decreasing the entire time to the right of 11 over 2. If all you have is an increasing interval followed by a decreasing interval, then it must be an absolute max, not merely a relative max. Here's how you word that. Since p prime is positive on the interval from 0 to 11 over 2, and p prime is negative on the interval from 11 over 2 to 17, p reaches its maximum value at x equals 11 over 2. Don't forget about the y value. We need to find that too. Let's go back and say at x equals 11 over 2. So now we can plug in this value for x. So y is equal to negative 11 over 2 plus 17. 17 is 34 over 2. So y equals negative 11 over 2 plus 34 over 2. In other words, y is equal to 23 over 2. Make sure you answer the actual question in your closing statement. The two numbers that maximize the product are 11 over 2 and 23 over 2. Number 2. What point on the graph of y equals x squared is closest to the point 3, 1/2, which is this point right here? So we need to pick the point x, y that minimizes the distance illustrated by this orange segment. The primary equation is an equation for the quantity you are trying to maximize or minimize. In this case, this distance. In Algebra 1 or geometry, you should have learned that the distance between 2 points x1, y1 and x2, y2 is given by this distance formula. So, using the distance formula, the distance between these 2 points is given by this expression. This is the primary equation, the quantity that we need to minimize. Something that is unique to optimization problems is the fact that we have to make up this letter. So students are not used to that, and sometimes they want to set it equal to 0 or something, but we had to make up this letter D representing the quantity that we are trying to minimize, and then we had to set the expression equal to that made up letter. So it didn't have to be D, you could pick another letter, but it had to be something. The secondary equation, they just gave it to us. Y equals x squared is the secondary equation. We use the secondary equation to rewrite the primary equation in terms of a single variable. That's always the goal. The primary equation has to be rewritten as a single variable. So let's plug in x squared instead of y. Normally it would be time to find d prime and make a d prime sign chart. However, this is a really ugly equation to take the derivative of. We have chain rules inside of chain rules inside of chain rules. So there's a shortcut that we can use when we have a problem like this with a big square root over it. We can make up a new letter to represent the expression that's under the radical. I'm using the letter I to represent the inside part of this expression. If we can find the value of x that minimizes the inside part of the expression, that same value of x will minimize the entire expression. So let's find I prime and make an I prime sign chart. We need a little bit of chain rule here, so the derivative of the outer function is this. The inner function is x minus 3, and normally I would say now multiply by the derivative of the inner function, but the derivative of x minus 3 is 1, so we don't need to write that down. Let's do the chain rule for the second term. The derivative of the outer function is this, while the inner function is your x squared minus 1/2. This time we will write down the derivative of the inner function, which is 2x. 2 times 2x is 4x. I'm going to do the distributive property to get rid of these parentheses. I'm hoping we can combine like terms and simplify. Distributing the 2 and the 4x gives us this, but now we notice that we have a 2x and a minus 2x. So those cancel each other out. So I prime is equal to 4x to the third power minus 6. Now we need to find the critical values of I, which is where I prime is equal to 0. A polynomial is always defined, so we don't have to worry about where I prime is undefined this time. So setting this equal to 0, I'm going to go ahead and move the 6 over. So we're going to have 4x to the third power is equal to 6. Dividing both sides by 4, we get x to the third power is equal to 6 over 4, which is 3 over 2. And taking the cube root of both sides, we get x is equal to the cube root of 3 over 2. Not very pretty, but we have one critical value. Now we make the I prime sign chart with the one critical value. Make sure you label it as I prime. We need to decide whether this factor is positive or negative in each interval. 4x to the third power minus 6 is equal to 0 right at this critical value. For values of x to the left of this number, well, let's see. We could pick 0 as a test value. If we plug in 0, we would get negative 6. So negative in this first interval. What about values bigger than this? I'm not sure exactly what this number is, but if we plug in 2, for example, 2 to the third power is 8. 8 times 4 is 32. 32 minus 6 is positive. Normally, a sign change from negative to positive on an I prime sign chart would only tell us that we have a relative minimum at the cube root of 3 over 2. However, this is a special case. Because we only have the one critical value on the entire domain, we have divided the domain into just 2 intervals. Because I prime is negative to the left and positive to the right, we know that I itself must be decreasing from negative infinity to here, and then increasing from here to infinity. Therefore, we must have an absolute min at the cube root of 3 over 2. Remember, the actual quantity we need to minimize is this distance d. Because we made up this expression I for the inside part and we minimize that, we need to add in this extra phrase to link it back to the actual quantity d. We say I, thus d, reaches its minimum value at x equals the cube root of 3 over 2, because I prime is negative on the interval from negative infinity to cube root of 3 over 2, and I prime is positive on the interval from cube root of 3 over 2 to infinity. One more time, because I prime is negative on the entire domain to the left of cube root of 3 over 2, and positive on the entire domain to the right of cube root of 3 over 2, we know that I is decreasing to the left and increasing to the right, and therefore has an absolute min at the cube root of 3 over 2, rather than merely a relative min. So we found the x-coordinate that minimizes the distance, but don't forget about the y-coordinate. Let's find y at x equals the cube root of 3 over 2. Actually, let's rewrite this as 3 over 2 to the 1/3 power, which means the same thing as cube root. Y is x squared, so to find the value of y, we just need to square this. When you raise a power to a power, you multiply. So we're going to have 3 over 2, but 1/3 times 2 is 2/3. So that is the y value that goes with this x value. Make sure you answer the actual question with a closing statement. We are supposed to find the point on the graph of y equals x squared that is closest to the point 3, 1/2. So here's our closing statement. The point closest to 3, 1/2 is 3 over 2 to the 1/3 power, 3 over 2 to the 2/3 power. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.